Done. You have to connect to the Wi-Fi here. Yeah, it's already connected. Yeah. Yeah, Zoom is working, I think. Yes. Zoom is working, and we stick ourselves to this one. Otherwise, you're gonna need to restart your machine like this. And question. Oh, yeah. So in Malayo. And oh, see song now. Next person. We need the next person right here. Yes, check it right there. It's YouTube. YouTube. Oh, please, YouTube. Yes. Okay. Finish and build share, right? Build share. Electron started. Right, it's gone. And this one, right? Yeah. We need to go live like this. Use another account. Log in. YouTube. Yes, this one. And once you connect you YouTube, create event 16. Yes, sir. And this one go live. 3 people already turned on up. And right here, you have to check this here, please. Yes. Now public just in. There are 3 channels. You can check it here. 3 channels. Exit 3 channels. And yes, please go there. Oh, my error. Master title is invalid. Okay, Yahweh. This is Zoom, I think. Yes, it's Zoom, right? Not made for kids. Oh no, why not? This is Zoom channel, right? Zoom channel. Yes. And for the people who want to go to get into theเครื่องนะครับแป๊บนึงนะครับต้องรีสตาร์ทใหม่ค่ะ I treat lesson ตั้งชื่อยาว Steam laptop yes let's get into, this is the Zoom version. I have to go to this one. Where is that? Okay, this one. โอเคชัยสิทธิ์พิมพ์ชื่อมาแล้วครับเดี๋ยวนะครับเครื่องนี้มันมีปัญหานิดนึงครับคือชื่อตั้งชื่อยาแล้วมันไม่ไปครับหยุดก่อนดีกว่านี่หยุดโอเคสตรีมครับไปตั้งชื่อยาวเขาครับ go live next YouTube create event in here F3 no stream that only yes go live I hope it works now. Yeah, okay, it works great. All right. So good morning, everybody. Good afternoon, everybody. We are late in 7 minutes. Team is inactive. What's the problem? Okay. Yes, we will continue our story here. Once you finish it last time, the detail of standard model of elementary particles, like which serve as many basic things in physics, right? Even the elements in space, it is based on several particles here. What you have seen in this table, the elementary particle, and let's check the internet connection to this device. Yeah, it's already correct. All right. Okay. Yeah. The next thing is that there is another physics theory that could explain something about the behavior of the wave particle of any object, right? And that idea came from a French physicist in 1924, Louis de Broglie. Okay, I don't know how to pronounce it exactly, but Louis de Broglie, maybe you can pronounce like that. He presented a new idea in his PhD thesis. Okay, only at the doctoral degree level. Okay, in PhD thesis only. Okay, with the same kind of these, you can also do that. Okay, if you are eager, you want to pursue the PhD or the doctoral degree at a university. Okay, you don't need to be in a high level like in the in a professor level or something like that. Yeah. Louis de Broglie has presented an idea which is quite different from many works in at that time. Okay, in yeah, because he wanted to he wanted to explain the behavior, the wave behavior of several particles, especially the tiny particle like something on the atomic scale. Okay, something with radius of angstrom, right? It is 10 raised to negative 10 meter. Okay, a free electron with mass m moving with speed v. Okay, if you have a very tiny particle, this his theorem is very good to explain something which is very tiny, like electron, right? Electron is moving with speed v. Okay, let's say this is the mass of electron, which is 9.1 10 to the negative 31 kilogram, right? He said that this is a particle, a very tiny particle. It's a kind of lepton actually here. Electron belongs to the class of leptons, right? As you know from the elementary particles in that standard table. Yes, the electron here is moving with speed v, and the boy said that these particles also generate a wave, okay, electromagnetic wave with the wavelength lambda, and he proposed that of course from the classical physics, the momentum of this particle could be found by the conventional expression, right, which is P. Okay, P stands for momentum, and M, right, on the right hand side, P equal to M times V. M is the mass of the electron, and V is the speed of the electron particle. So that's the classical way of the momentum, right? You heard that before in Matheum 4 or Matheum 5, right? And yeah, it's exactly the same way as the photon, which is described by lambda is equal to h by p. And once you substitute p by mv, you're gonna get lambda of electron that also generate the wave. Where is the color change? Okay, here. This electron would generate also the wave, okay, and the wavelength here of this one could be found from this expression. Lambda is gained by h by mv. You know h, right? H is the Planck constant that you have seen before, right? We have seen before, which is on the scale of negative 34 or something like that, right? That's the Max Planck constant. Yeah, before that, in the topic of photon and so on. Why do we have this? Why? Oh my God. Oh. Where is the Planck constant? Oh, here. Okay. The Planck constant is the 6.6260715 times 10 to negative 34 joules second, right? And that's the typical scale, typical unit. And if you want to express it in the appropriate scale, like in electron scale or atomic scale, it's going to be reduced by divided by 1.6 10 to negative 19, right? And the quantity of Planck constant will remain like 4.1 10 to negative 15 electron volt second, right? Yeah. And yes, here you can just simply use the Max Planck constant to this one, okay? And the mass is the mass of any particle. And at the first stage, Louis de Broglie has observed this behavior to electron, right? And but this expression is valid to any particle, whether it's big or not, okay? And yeah, yes, you can use this expression to anything, okay? Even bigger, it's also available, okay? It's also valid, like the object in a bigger scale, like tennis ball, right? Tennis ball, which is big, much bigger than the electron. Okay, it's also possible to apply this formula, but the important thing is that once you know that H is on the scale of -34, 10 to -34, and if you have more mass, right, the wavelength, okay, mass appear as the denominator, the wavelength will be very, very tiny. And once you have very tiny wavelength, it is very hard for human at the moment to have any measurement device to observe this. Okay, and that's the limit right now. But if you have small, very small amount of mass, like the tiny particle, for example, electron or any particle in this table, so in that case, yeah, it may not hard for human to detect the wavelength of this duality, which is called wave particle duality. Okay, the two phenomena that appears from the particle movement, right? And that's called duality of wave and particle. Okay, and that's called wave particle duality. Okay, which has the expression like this: H equal to M divided by MV. Okay. Furthermore, the boys observed that this relation is valid through many kind of particle, not only electron, right? It's valid also to protons, to any particles that you may have seen in the standard elementary table. Okay, so yeah, that's the generality of the expression by Louis de Broglie. Yeah, now let's get into the first example so that you can see the idea how we could apply the Louis de Broglie. Oh, that's very far. Okay, the Louis de Broglie expression lambda. Oh, it's too far. Yes, this is the kind of modern physics, right? We are talking about the idea of wave particle duality, and the next thing is going to be the Werner-Heisenberg principle of uncertainty. Okay, we will talk about that later. I would not waste our time to do that. Okay, this example asks us to find the speed and the kinetic energy of a neutron. Okay, that has the de Broglie wavelength as 0.2 nanometer. Okay, it's in the opposite way, right? Yeah, usually we need to know first the mass and the velocity or the speed of that object first, and then we're gonna get the output or the outcome as the wavelength, right? This wavelength is called de Broglie's wavelength. Okay, yeah, but in this example, it asks us something in the opposite way. Okay, in the reverse way. Okay, yeah, and let's talk about that. Yeah, the speed and the kinetic energy, right? So we draw here a paper in yes, it's something about neutron, right? And neutron is going to be what is the notation of the neutron? I forget that. Okay, neutron is 0 and 1 here. Okay, there is only positive charge. Single single element here at the superscript, and there is no charge at all, right? There is no charge, and one element here. Yeah, neutron has the mass of 1.67 times 10 to negative 27 kilogram, right? That's the mass of the neutron, and yeah, that's the basic quantity we need to keep in mind. And what they say is that okay, they want to know the speed of neutron. What is that? And furthermore, they want to know the kinetic energy of the neutron. And what is that, right? Given the de Broglie wavelength of the neutron 0.2, or in the SI scale, you're gonna have 10 to negative 9 meter, like that. Okay, you convert it to the SI scale already. All right. Yes. Let's get back to the de Broglie wavelength expression. Lambda equal h by mv, right? This one, equation 57. Lambda equal to h by mv, right? But in another term, you're gonna see that if you convert it to, because we need to deliver the first answer, right? We will be h by m and lambda, right? Yeah, you will get this expression, and you could find the speed or the velocity for the neutron particle like this, right? You just substitute the mass of the m here as the m here as the mass of the neutron. You could get Vn, right? For the second quantity, Kn, okay, you know that Kn is the kinetic energy of the neutron. Okay, this particle is moving with speed Vn, the velocity or speed of neutron, and m is mass of neutron, v speed of neutron. But once you take a look at the first equality in equation 57, you know that lambda is h by p, right? And you could solve this equation for p, which is the ratio between h and lambda, right? And we're gonna find the relation between the kinetic energy and the momentum, right? Yeah, as we know, P from equation 56, P is equal to M and V, right? But what we have here is only mv, right? Mv squared. So if you write down further, it's gonna be 1 by 2 mn vn. Oh, sorry for that. Okay, mn vn squared. But if you write it like this, it means that you have m squared, right? Which is not correct. We have only a single m without any square, right? So we're gonna divide this one by mn. Okay, and yes, of course, it's gonna remain 1 by 2, and p momentum of the neutron by mass of the neutron. Okay, if you take a look at this, okay, so we could get the you can calculate it in many ways anyway. Okay, you can also calculate first the velocity, and after that you substitute velocity to the expression, and then you just kinetic energy, and then you substitute the mass of the neutron. Is also possible, or you wanna calculate first the momentum, and then you substitute the momentum to the expression. It's up to you. Okay, I just show you several ways to reach the destination or the answers. Okay, so let's get into the first quantity, the speed of the neutron, right? So you know that h is 6 blah blah blah. Yes, h is 6.626 times 10 to negative 34, and you divide this one by the mass of neutron, and you just take a look at that one, right? It's 1.675 times 10 to negative 27, and that's in the kilogram scale, right? H and M and lambda is the wavelength, which is stated here, 0.2 nanometer, but you have to use the typical scale, the SI scale, which is 0.2 times 10 to negative 9, right, meter. And you put it into the calculator, you're gonna get somehow like 1,977 times 9, and the unit for the is meter per second. Okay, and that's the speed of the neutron, this particle. Okay, and you know that the Brown wavelength is valid for several particles, right? Several types of particle. And yes, the next thing is that we need to calculate the kinetic energy for a neutron, right? Kn is 1/2. Mass of the neutron is over there, right? Which is 1.675 times 10 to negative 27. And v square, v is the speed what you have got. You have just recently got 0.9 n square, right? And you leave it into the calculator. I don't understand. You leave it into the calculator, you're gonna get somehow like 3.277 joule, right? The unit of the energy or the work is joule, right? Yeah, you get something like this, but no, but there is also 10 to negative 21, which is very, very tiny, right? The energy on the order of 10 to negative 21 is very small, so it's not appropriate. Okay, if you work in a bigger scale, like the engine of the car or the power in several big projects, okay, the energy is not going to be so tiny like this. Okay, then it's appropriate to use the unit of joule. But once we are considering the tiny particle, for example, neutron, we need to use the more appropriate unit, and we divide this amount, this quantity, by the electron charge, 1.6 times 10 to negative 19. So we get more appropriate unit for that, right? So once you divide this one, say 3.277 times 10 to negative 21, divided by 1.6 times 10 to negative 19. So you're gonna get, once you leave it into the calculator, right, you get 0.02, and it's in electron volt. Okay, and that's the units of the energy you could get due to the movement of the neutron. Okay, and that's called kinetic energy. All right. Yeah, we have already considered the tiny particle, right, like the neutron. Okay, so what about the big particle, like baseball? Okay, I guess that the author of this example would be in the United States of America, because baseball or American football are quite popular there, right? In the United States, right? But for us in Thailand, I'm not sure whether it's popular or not, right? Okay. Yeah. Let's talk about the baseball scale. Okay, this is the visible object by eyes, right? That's the object we could see by eyes. So let's say this is the ball, right? And it's called baseball. Right? Compare the bright wavelength for an electron. Oh, it's tiny. So let's say if this one is electron, right? And this one is the baseball, right? This is the baseball BB. Okay, baseball is much bigger than electron, right? And electron with this amount of mass moving at the speed 1 times 10 to negative 7 meter per second, and the baseball is moving at the speed not so high like that, okay, not so fast like the electron, okay, but anyway, it's 45 meter per second, okay, 45 meter per second. And what about this quantity in the most noticeable unit? For example, in kilometer per hour, what is that? 45 meter per second. So if we want to convert these ones, so let's say this is Fermi, right? Fermion. This is Peter Higgs, who discovered Higgs boson, right? And this is the Bose. The physicist used his surname to say to call another one type of the particle, which is boson, right? So and this Fermi, okay, let's say 45 meter per second to kilometer per hour. My God, I'm still 45 meter per second to kilometer per hour. You can see that the baseball speed is 162, right? And you may have watched the tournament of baseball competition or something like that, and the speed of the baseball is like in the high speed of the car, right? It's on at that level, 162 kilometer per hour. Any of you who would have ever sit into the car with this speed? Is there any of you who have ever experienced this speed in car or in any train? Yeah, if you have ever gone or visited some countries like Japan, in France, in Germany, in some other countries, you may have ever got into the high-speed train, or even in China, they would have the speed sometimes if they use the magnetic force, and there is no touching point between the railway and the train could go up to 400 kilometers per hour. That's very high speed. But for the general train that uses electricity, it's quite simple to reach this speed, right? 162. Okay, yeah, the baseball move with 45 meter per second, or in kilometer per hour, it's 162, right? Approximately. So you could see that the big object could not go. Oh no, it's not. It's positive, right? It's not so high as the tiny particle, which is electron, right? But anyway, mass of electron is 9.1 times 10 to negative 31 kilogram, right? And mass of baseball is much bigger, much heavier, right? It is 0.145 kilogram, right? Yeah. The question from this example is the comparison, right? They asked us to make the comparison between these two objects, right? The small one and the bigger one, right? So yeah, from the boy's wavelength expression, lambda is given by h is given by h divided by mv, right? This expression h divided by m and v. So yeah, let's talk about electron first. Electron first. All right. So lambda of electron will be h. Which is 6.626 times 10 to negative 34 and Joule second, right? That's the unit for the Planck constant. And the next term is the mass, right? The mass of that object. And once we are talking about, once we are considering electron, we're going to use 9.1 times 10 to negative 31 kilogram. Okay, and the next thing is the speed, right? The speed of the electron that is moving. So it's 10 to 7. 10 to 7 means 10 million. Okay, 10 million meter per second, which is very, very high. Okay, for the human movement, I think human movement could not reach that amount at all. Okay, and then you put it into the calculator. So to save time, I'm going to use the result from the lecture notes, right? Because we waste our time during the setup. And yeah, the wavelength of electron is going to be 7.27 times 10 to negative 11. Okay, negative 11 meter. So let's ask or let's consider whether it is possible or not to detect the wavelength on this scale. I would say it's not so far from the human ability, because human ability could detect the light, and the light is on the scale of 10 to negative 9, right? That's the light frequency wavelength, right? 10 to negative 11 is only 2 finer order from 10 to negative 9. So it's not so far from the human ability to detect the wavelength caused by electron moving at this speed. Okay, now let's consider the next thing, which is the baseball, a bigger object, right? Baseball. The lambda for BB baseball will be, of course, the same thing. The numerator is the Planck constant. In the SI scale, 6.626 times 10 to negative 34 and Joule second in divided by the mass of the baseball, right? Mass of the baseball is over here. They just provide 0.145 kilogram. Okay. And the next thing is the speed. The speed is not so high. It's only 45 or 162 kilometer per hour, right? Yeah, and that's, oh, sorry for that. 45 meter per second. So once everything is in the SI scale, we could immediately calculate it. Okay, put it into the calculator, and we're gonna get the lambda for the baseball as 10.016 times 10 to negative 34, okay, and meter, okay. And let's consider the reality. Negative 10 to negative 34 is a very, very tiny amount in at the moment, okay, in 2021, at this year, no apparatus, no measurement device could detect the wavelength on this scale. Okay, you can use the formula and you can calculate it. You can see the theoretical value, but in physics we have to also consider the reality. And on this scale 10 to negative 34, there will be no measurement device that could detect the wavelength of the electromagnetic wave like this. Okay, it's not possible right now, but anyway, you could see the idea that the wavelength predicted by de Broglie for the tiny particle that moves very, very fast, 10 to 7 meters per second, is in a considerable scale that human could detect. But for the bigger scale baseball, which is a kind of a particle, right? It's big. It could be observed by human eyes, but the wavelength that emerges is beyond the ability of human to detect, is 10 to negative 34. Okay, so the comparison is the following: the wavelength of the baseball is much shorter than the wavelength caused by electron movement. Okay, and yeah, and the next question is compare this wavelength with that of an electron traveling at 0. You would see the full name of the full text of the example, traveling at 0.999 z. Okay, you know z is the speed of the light, right? And what about the wavelength caused by electron? Once electron is moving almost at the same speed as the light, okay, but before that I would say no particle could be faster than the speed of the light. Okay, the speed of the light is the limit of the velocity or the speed of any object. Okay, but what about the wavelength caused by the movement of the electron at this speed? So once you talk about the particle that moves very, very close to the speed of the light, we are going to need to deal with the relativity theorem, which is proposed by Albert Einstein. Okay, I hope that you have ever seen the theory of relativity by relativity theorem by Albert Einstein, right? ทฤษฎีสัมพันธภาพนะครับคุณเคยเห็นเนาะ and one of the quantity from the result by Albert Einstein is the relativistic momentum. Okay, relativistic momentum, and the formula, the general formula of the momentum is like this, right? It's P equal mv, right? And that's the classical expression for the momentum, right? But for the momentum of the object that has speed close to the light, you're gonna need the relativistic momentum expression, which is a little bit more complicated than the typical formula for I'm not sure what about the people in Zoom. Is there anyone who wants further to get into the Zoom classroom? No, huh? Okay, yeah, the momentum expression in relativistic theory is this one. Okay, it's Yes, of course, it's the ratio relative. If V is okay, the denominator just emerges, right? If you move with the speed of light, you're gonna have C by C as number one, and this is 0, and your momentum is gonna be infinity, right? So that's valid for only the photon, but the photon has no mass. Okay, photon has mass of 0, so 0 times infinity is going to remain 0 too. So momentum of photon is nothing, right? But for any particle, you're going to need to substitute the mass of that object and the speed of that object too, right? In this one, and yes, you may calculate first the momentum, right? And if they ask you about the momentum, but it's not the case because they want to know the wavelength of the electron at that speed, right? The wavelength of the electron at the speed is going to be this de Broglie is going to be given by the de Broglie expression h divided by mv, right? Yeah, h by p. Oh, sorry, but p here is going to be this one from the relativistic theorem by Einstein. You substitute this one into this expression, you're going to get here this one, right? This expression, and everything. The mass should be the mass of electron. The velocity should be the velocity of the electron, right here. Okay, and this is the cascaded ratio, and we move the denominator here to the upper part, right? We're gonna have this one here at the numerator, and yes, we will substitute sort quantities into that expression. Yes, here. Yeah, lambda of the electron, right? Lambda of the electron will be h by me and ve, right? In square root 1 minus v of electron divided by c and square, right? So let's substitute everything, which is 6 to 6, 10 to negative 34, and here the mass of electron, which is 9.1, 10 to negative 31, and the velocity, which is the 0.999, okay, and the speed of the light, which is 3 times 10 to negative 8, and the square root 1 minus, and of course you know that VE, the velocity of the electron, is 0.99, right? Once you divide it by C, you're going to have 0.999 square, okay? And once you leave these whole numbers into the calculator, you're going to get the wavelength caused by the electron at this speed as 1.086 times 10 to negative 13 and meter. And yeah, you can see that the wavelength of the electron at this speed, okay, which is very close to the speed of light, is a little bit, is even smaller than the speed of electron at 10 to 5, right? 10 million meters per second, right? Yeah, it's even harder for us to detect the wavelength of the emitted photon caused by electron here. Okay, in หมดเวลาแล้วหรือยัง it's 1350, right? We're gonna reach our limit, right? Yes. In 1927, Davidson Gamma at the Bell Lab, right? Bell Telephony telephone laboratory discovered the electron diffraction. Okay, not only wavelength caused by electron movement or electron speed. Okay, further behavior of tiny particle movement is independently observed by these two researchers, Davidson and Gamma at Bell Lab in the United States. Let's switch to the European continent. In Germany, Esterman and Stan demonstrated the alpha particle. Okay, alpha particle is the helium atom without electron at all. Okay, without any electron at all. That's called alpha particle. The alpha particle has also diffraction, and that's discovered by Esterman and Stan. Okay, you could see some detail of the discovery by two independent groups of researchers here in the United States and in Germany. More experiments revealed that the diffraction of low energy neutron and large molecules, okay, even the large molecule could have also diffraction behavior, and neutron with low energy could have also the diffraction behavior. All of this discovery gave a strong support to de Broglie's hypothesis. Okay, the idea of de Broglie is only the hypothesis. Okay, the idea on the paper, but no one have proved that. Okay, before 1927, no one confirmed the de Broglie idea is valid in reality. Okay, we have calculated so many things, the wavelength and so on, but in 1927 and so on onward, right, the people have made or discovered something that could verify the truth by de Broglie, right? All of this discovery gave a strong support to de Broglie's hypothesis, and and that's the whole story of the wave-particle duality by de Broglie's wavelength expression. Now we move to another tiny particle phenomenon, which is discovered by Werner Heisenberg. Okay, Werner Heisenberg is a physicist in Austria, right? In Austria, he found an inequality of the product of I'm not sure it's German or physics. Werner Heisenberg. Yes, he is German. I'm sorry for that. Yeah, Werner Heisenberg is a German physicist, and he proposed the idea, right? Because when you are dealing with the particle, which is very, very extremely small, it's really hard for us to detect, right? And in reality, the physicists like Heisenberg has discovered there is no exact point for the tiny particle at all. Not all the electron. Okay, for any particle that is extremely small, what we could say is only the prediction, and the prediction should have mean value and the difference of the possible location of that object, and that's called uncertain coordinate x, okay, of any object. Let's say if you stay here at the point, the reference point, and you see the particle like electron, and you could not measure the exact location of electron at all. But what you could see is only the delta x location. Okay, electron should be in this range. Okay, and the momentum, because the tiny particle would also move, right? So the momentum could not also be predicted simply by that one. Okay, and what the physics could predict is only the corresponding uncertain momentum, and that's called delta px, right? Delta px is the uncertain momentum of the tiny particle. Whatever particle you are watching, whether it's neutron, proton, electron, or electron, neutrino, whatever that has mass, okay, it should follow this expression. What about this expression? The expression by Werner Heisenberg is delta x, delta px, okay, the uncertainty along the x-axis is greater than h by 4p and 1 by 2, or you know that h slash is h by 2 pi, right? In terms of h slash, which is the reduced Planck constant, it's going to remain half the reduced Planck constant 1 by 2 of h slash, right? That's the Werner Heisenberg expression. Okay, it's unfortunately we could not find the exact location of the tiny particle. Okay, it means that in general, neither the momentum nor the position of any particle could be measured simultaneously and with arbitrary great precision. Okay, as classical physics would predict. Okay, for a big object like a car or your body, you could measure precisely, but it's not the case for the tiny particle. Okay, because this chapter is talking about something in the atomic scale, right? So it's tiny. So in order to completely understand the formula by Werner Heisenberg, we're gonna use the equation 65, right? For one example, an electron is confined inside a cubical box. What is that? It's a cubic box, like cubical box. Somehow it is, right? Okay, that's the cubical box. Yes, and one side of the cubical box is 1 meter, like this, okay? And of course, in other side, it's going to be 1 meter too. In this side too, right? 1 meter. And yes, estimate the minimum uncertainty in the x component of the electron momentum. Okay, what is that? Minimum uncertainty, so is delta px of the electron. What is that? And the kinetic energy of the electron with above momentum. So what is delta k electron then? Right. So we would go to the Werner Heisenberg expression. So we start from the Werner Heisenberg expression. It's delta x, right, and delta px greater than h by 4 pi, right, h by 4 pi. And what they want to know is the minimum, right, the minimum min. So what is the minimum of the delta px, right? So minimum of this one could be found by we move delta x to the right hand side, right? Delta px is greater than h by 4 pi and delta x2, right? The uncertainty location, the uncertainty location of the box, right? So it's going to be somehow like that, and that's the location here. H is 6.626 times 10 to negative 34, and 34, not 35. And joule second, right? In 4 pi, right? And the uncertainty of x, so delta x is one side of the box, here, so it's gonna be 1 meter too, right? So this one is 1 meter. Okay, you just put it into the calculator, you're gonna get the answer. Okay, okay, the minimum of 4 pi. What is that? Oh no, the side of the box here is not 1 meter. It's much smaller than that. It's okay. It's 10 to negative 10 meter and 10 to negative 10 meter too, right? And 10 to negative 10 meter too, right? Right here, yeah. So we are wrong here. We have to use 10 to negative 10 meter. All right. 10 to negative 10 meter. All right. And yes, we substitute that into this expression, and we're gonna get the result from the calculator, which is 5.273 times 10 to negative 25. And the unit of the momentum, as you know, is the product of mass and velocity, right? It's going to be kilogram and meter per second. And that's the unit for the momentum, right? The minimum momentum. So what is the kinetic energy corresponding to the above momentum, right? So yeah, you know that is 1/2 mv square, right? And you know before that P is equal mv, right? And if you multiply m and divided by m to this expression, you're gonna get m squared v squared by m, right? And yeah, once we know P is equal to mv, it's gonna be 1/2 P squared by m, right? So we're gonna apply this expression to the electron, right? Kinetic of energy will be 1/2 mass of electron. Oh, you know, it's momentum of the electron divided by the mass of the electron, right? So it's going to be 1/2 in 5.273 times 10 to negative 25 square and divided by mass of electron, which is 9.1 times 10 to negative 31. All right. And once you leave these numbers into the calculator, you're going to get the minimum of the kinetic energy, which is 0.952 electron volt. Okay, to convert the energy from the Joule scale to electron volt by dividing it with 1.6 times 10 to negative 19. Okay, you're gonna get the result in electron volt unit like this. Okay, and anyone who would like to join in Zoom? No, only shy this one, right? Yes. Let's get back to our story. We now reach the next example about the Werner Heisenberg uncertainty, right? The speed of an electron is measured to be okay, we consider the same particle, electron, right? 5 to 10 to 3, which is 5,000 meters per second. You could convert to kilometer per hour yourself from any calculator, and to an accuracy of 0.03 0.003%. So very tiny, and find the minimum uncertainty in determining the position of the electron. Okay. So what is minimum delta x? What is that? Okay, minimum delta x mean yeah, you could start from the general expression, general information given in this example. They say the speed of electron is measured to be, okay, the mass of electron. So delta V, right? Delta V of electron. Delta V of electron is found to be 0.003 by 100 times the speed, right? The actual speed is the actual speed of the electron is, this is the mean value, right? Which is 5 times 10 to 3 meter per second, right? And yes, that's VE, right? And you know from the Werner-Heisenberg, right? Werner-Heisenberg expression says delta x and delta px is greater than, is not equality, right? It's greater than h by 4 pi, right? And if you want to find a minimum of delta x, minimum of delta x will be equal to, you move px to the right hand side, you're gonna get h by 4 pi, right? And delta px, okay, delta px, and that's the uncertainty of the uncertainty of the momentum of any object along the x-axis, right? And let's consider delta px, which is m and v, right? But it's the uncertainty of the velocity of the electron. So this is the mass of the electron, right? So we're gonna substitute this one into that expression. So we get minimum of delta x as h by 4 pi and mass of electron and delta VE, right? So we will substitute everything into that expression. 6.626 times 10 to negative 34 and 4 pi times the mass of electron, which is 9.1 times 10 to negative 31, and the uncertainty of the electron speed is this one, right? So you, oh no, why, what happened? You can cancel this one, right? Cancel this, and you get 0.003 times 50 only, right? It's 50. All right, it's I don't know, 0.15, okay, meter per second. Okay, and that's the uncertainty of the electron speed, right? 0.15 meter per second. And yeah, that's the whole thing. Once you leave these numbers into the calculator, you're gonna get the result, right, which is it's approximately 0.385 and 9, okay, in millimeter, okay, and that's it for this example. So the time is over now. So let's finish our problem right here, and we're gonna have we need to have the, I don't know, the homework, right? The homework is something about when Heisenberg along the x location, or the, I don't know, yeah, Werner Heisenberg or the energy wavelength or the radius of the bigger atom, which is called hydrogen-like atom. Okay, I will create the homework template in the Google Classroom later. Okay, if you have any questions, so let's finish our lecture of today. So if you have any questions, just let me know. And if not, we're gonna see each other. Okay, Friday is the last day of the year, right? It's New Year's Eve, so we would not have the lecture, and see you next year. Okay, bye bye สวัสดีครับพบกันปีหน้าครับการบ้านเดี๋ยวสั่งใน Google Classroom ให้นะครับบ๊ายบายครับสวัสดีครับ It's not entertaining. Is entertainment. Yeah. Entertainment. Education. Just save it like this. Okay. This one, let's set it to be. Wait. Why? This. Okay. Maybe. Oh. Oh, yeah. Okay. Need to have some power from anyone. see this one. Put it to here. Yes. Oh, yeah. Lesen unterstützt. Was ist das? Oh. No, not this one. That's work perfectly. $14.10 is the time for the next. Yep, sorry. Yeah. Yeah. Wait. Okay. Should be so. My God. Yeah. You have to send this. Go. Go. 6048. 604. No. This. Wait. Screen capture. Where's that? Oh. Everything we just delete. Delete it. Okay. Right here. That's the answer scene. And now shrink.
from here we have Shawin until what? That's the reason why. Okay, let's go to the toilet. That's 19. Eventually, show OBS ni showing. Where are the yes. Yeah. Still. It's not raining. Oh. Please. To read small. Yes. With this you could. Oh. This one, right? You send it through meeting. Does it go? Oh, why? Oh my God. นานไป finish and let's get back to good notes and let's send this to
Okay, it's 14:12 right now, and this is the time for section 605. Yes. แบบกิ๊กใช้สวับสวอปไป1ใช้ไป2 กิกนะครับ Okay. Once everything is all right, if someone would like to join the Zoom session, just let me know. If not, we are going to go ahead in our YouTube channel. All right. Oh, ทำไมไม่ออกทำไมไม่ไปอ่ะก็ยังไม่ไปนะ Okay, this is the time for the M605 section, right? Which SCI33206. We move to another file for M605. Okay, I hope everything is fine. Stream health is poor. Stream health here. This one. Stream health here. ไปไม่ค่อยดีครับอันนี้ Good. This one is excellent, but the OBS channel is quite poor. Right. All right. Yes. This is the section. Okay, it's time for M605 right now. We need to start soon. And yeah, you have seen before, right? The standard table of elementary particles here. Okay, you have gotten to know the fermions, several kinds of fermion. You have got to know the several kinds of bosons, right? And you know that in fermion we could divide the particles into quarks and leptons, right? For bosons, there are two types of boson, which are gate boson or Victor boson, right? And it's known also. Another kind is scalar boson, right? And yes, now it's time to go ahead. Yeah, because the classical physics says that the particle, any particle, just follow the classical way of the physics, right? Whether it's momentum and so on, but there was an amazing physicist is called, his name is Louis de Broglie, right? Louis de Broglie มีใครเข้าที่ Zoom ไหมครับไม่มีนะโอเคLouis de Broglie has presented a new idea in 1924, okay, which was during his PhD thesis, okay, his doctoral degree thesis or dissertation, and he found that free electron with mass m, if it moves with the speed v, it should have the wavelength, okay, and with the relation to the magnitude of its momentum, the momentum of any particle in classical physics is p equal to mv, right? อ้าวทำไมไม่มีคน M605 นะครับไม่มีใครเข้ามาเลยนะครับโอเค 1420, right? We're gonna start at 1420. I'm sorry for that. Yes, 1420, not 1410. I forgot about it. And move the, let's set the most. Maybe not. Okay, let's continue our story. Yeah, in 1924, a French physicist whose name is Louis de Broglie, right? He suggested an idea about free electron with mass m, and it moves with the speed v. And from these two conditions, the electron should have a wavelength denoted by lambda, and the wavelength is related to the momentum, and it's exactly the same way as the photon, okay, which is described by lambda is equal to h by p. Okay, lambda is equal to h by p, and if you substitute p by the classical expression of the momentum, it's going to be mv, right? So lambda is h by mv, okay, and yes, we could apply this formula or the expression to bigger particles or any kind of particles. For example, the small one, right? It's lepton, right? It's electron. Electron is a particle of leptons, right? So yeah, this expression, the de Broglie expression, is valid for electrons, for protons. Okay, proton is made of quarks, right? The up quark and down quark, and any kind of particle. Okay, and yes, okay. Let the mass of a neutron be 1.675 times 10 to negative 27, and that's the mass of the neutron, right? We know from the previous table right here. Okay, we know from this table that the mass of the neutron is this one, right? It's 1.67, right? Something blah blah blah, and 49 could be approximated as the number 5, right? And yeah, that's the value of the mass of the neutron as an approximation. If the mass of the neutron is on the scale of 10 to negative 27, okay, electron is on the order of 10 to negative 31, right? Yes, we could determine or use the de Broglie expression, right, to this thing, because neutron is a kind of particle, right? Okay, find the speed and the kinetic energy of the neutron that has the de Broglie wavelength of lambda equal to 0.2 nanometer. Okay, yes, in order to solve this, let's open a new page. Yes, what we know, the information we know is the mass of the neutron. The mass of neutron, Neutron, mass of neutron in Mn, right? Let's say Mn is 1.675 times 10 to negative 25. 27, sorry for that. 27 kilogram. Okay, that's the mass of the neutron, the first variable we know. And they want to know the speed, right? So what is Vn in this scenario? In given the wavelength by de Broglie, lambda of the neutron is 0.2 nanometer, or in terms of the general meter, which is the scale of the SI system, right? It's going to be 0.2 times 10 to negative 9 and meter here. Okay, yes, the way to compute the speed of the neutron. Okay, this is the neutron with zero charge, and one particle in the nucleus. This is the number of particles at the nucleus of any atom, right? These neutrons move with the speed Vn, and they want to know what is the speed of Vn. Once we observe the wavelength emitted by this movement of neutron as lambda n equal 0.2 nanometer. Okay, in order to solve, in order to find the velocity, we're gonna manipulate this expression, right? We move v to the left hand side and we move lambda to the right hand side. So you will end up with Vn equal to h by m lambda n, right? Mass of the neutron too, right? Because all three variables have the subscript of n and เดี๋ยวนะครับดูที่ Zoom นะครับมีใครจะเข้าไปเอ่ยไม่มีนะครับโอเคyes the mass of the neutron is there is on the order of 10 to negative 27 and the lambda, the wavelength of the neutron is 0.2 nanometer. And yes, we compute this, right? Velocity of the neutron will be first the value of the max Planck constant, right? It's going to be 6.626 approximately, right? 10 to negative 34 and 2 seconds, and divided by the mass of the neutron, which is 1.675, 10 to negative 27 kilogram. And then the wavelength of the de Broglie, the wavelength of de Broglie, which is 0.2 times 10 to negative 9 meter, right? You put all these three numbers into the calculator, you're gonna get somehow like 1977.93, and that's the speed, right, meter per second for the neutron movement here. Okay, the neutron is moving with the speed of almost 2000, right? 2000 meter per second, right? If you convert it to the kilometer per hour, is even more than this number, right? So that's the first application of the de Broglie expression, de Broglie wavelength expression. Now we arrive at the second example about de Broglie wavelength expression. Please note that de Broglie expression is only the prediction. Okay, he predict that there should be this and this, right, from the theory only. Okay, from his PhD thesis or dissertation, and at that time there was no measurement that confirms whether the idea or the expression of de Broglie is really correct or not, right? Yeah, but anyway, there should be something like that. Yes, the second application of the de Broglie is this term de Broglie wavelength for electron. Right? Compare the de Broglie wavelength for electron. Okay, the first element is electron. It's moved with speed 10 to 7 meter per second, right? That the speed of the electron in, of course, the mass of electron is 9.11 times 10 to negative 31 in kilogram, right? Yeah, and that's the mass of the electron. And the next thing is the second object is the baseball, right? They want to observe baseball with a mass of less than 1 kilogram, right? So this is the baseball. Okay, the baseball object. It moves with 45 meter per second. Move with 45 meter per second, and the mass of the baseball is 0.145. The number is quite close or identical, right? 45, 4 and 5. Okay, the mass of the baseball is 0.145 kilogram, right? And they asked us to compare the Broglie wavelength of these two object movements. So from this information, we need to find lambda of the electron movement. What is that, right? In here, we're gonna need to find lambda of the baseball, right? What is that, right? So, and once we obtain the two values of the wavelengths or the Broglie wavelengths, we need to compare how is it in reality, right? How are those in reality? So just how to do that? Let's get back to the Broglie expression. The information we know is M and V, right? This is V baseball, and here is the speed of the electron, right? VE. So we know the speed and the mass and the Planck constant is not difficult at all. So we need we can use this expression, right? So let's get into the detail of the Broglie wavelength for electron, right? So lambda of electron, oh no, speed. Yeah, we need to find the lambda, right? Sorry, correct. Is given by Planck constant, right? It's 6.626 times 10 to negative 34, and it's joule second, and it's divided by the mass of the electron, right? Mass of electron is 9.11 times 10 to negative 31 kilogram, right? And the next thing is the velocity, the speed of the electron, which is quite high, 10 million. Okay, it's 10 raised to 7 and meter per second, right? In yes, you just put all these three numbers into the calculator. You're gonna get the result from here, and it's equal to 7.27, and it's in meter, right? Oh, sorry, there's also some multiply number. 10 to negative 11. Okay, it's less than angstrom. It's yeah, somehow this. And let's make a discussion. Let's discuss the possibility of the measurement of this scale of the wavelength caused by electron movement. Well, you know that the light has the wavelength on the order of 10 to negative 9, right? And yes, for the wavelength caused by electron movement, it turns to be 10 to negative 11, and yeah, this is finer, this is smaller or shorter than the wavelength of the light by 100. So it's still in the scale that could be measured by human, right? So yeah, that could be possible for human to detect the emitted photon like this, okay, caused by electron. And for the baseball, we go ahead with the baseball situation. Baseball, right? So lambda of baseball will be again the same thing, 6.626 times 10 to negative 34, in 2 seconds, right? It's divided by the mass of the baseball, which is 0.145 kilogram, right? Which is much bigger and greater than the mass of electron, right? And the velocity is smaller because the big object could not move quickly. It's 45 meters per second only. Okay, this one is 45 and 10 millions. Okay, it's not comparable. It's much slower than the electron, and 45 meters per second, right? And we put all these three numbers into the calculator. We're gonna get the value of the broad wavelength due to the baseball movement. It turns to be 1.0155 times 10 to negative 34. Okay, negative 34. You could see that the tiny amount, tiny factor here, 10 to negative 34, is caused by the Max Planck constant 10 to negative 34. And once it turns to be approximately 1, right, times 10 to negative 34 meter, you could see that it's very tiny amounts, and it's not easily detected. It cannot be easily detected, even could not be detected at all, right? Because it's too small for any measurement device to observe this. Okay, and it's not easy at all, right, to detect this. So that's the wavelength by the baseball, right? And we could compare. This one is 10 to negative 10 to 23 shorter, okay, shorter than the wavelength caused by electron, and it cannot be detected at all. Okay? It cannot be detected by human measure devices at all. And let's move to the next question. Compare these wavelengths with that of an electron traveling at 0.999 c. C is the speed of the light, 3 times 10 to 8, right? The third particle, actually it's not the third, the second particle. Another particle is still the same electron, but it's moved very fast. The speed of electron right here is almost 0.99 c, and denote that c is the light speed, right, or electromagnetic speed. Light speed is in the c is equal to 3 times 10 to 8 meter per second, right? Yeah, you could see that is a large amount of speed. In the previous situation, the electron just moved only 10 to 7, right, 10 millions, but this one is almost 300. I would say it's almost 300. 3,000 million meter per second, which is very fast. Just we are gonna need to compare the broad wavelength again, but in the classical way, if the particle doesn't move so fast, okay, not so quickly, we're gonna have if the particle doesn't move so far, we just simply use the general expression of the de Broglie, which is h by p, right? The Broglie expression is valid for any particle, any range of speed. But once the object moves very fast, like this one, which is very close to the speed of light, okay, 0.999, it is very close to the speed of the light, which is 3 times 10 to 8 meter per second. So we have to use the relativity theorem, okay, or in Thai it's called ทฤษฎีสัมพันธภาพนะครับเห็นไหมก็คือit is the theorem proposed by Albert Einstein. Okay, Albert Einstein found that if any object that moves very quickly, we the classical expression of the in the physics is not valid anymore. We have to use another complicated one. And as you know, in classical physics, you have P equal to mv, right? But for relativity theorem, says P becomes mv divided by square root 1 minus v by c n square. All right, and we have to use this expression when the velocity is closer to the speed of the light. Okay, when the speed of the object is close to the light, we have to use the relativity theorem. For example, the expression for the momentum is not simply like that. Okay, that's the classical physics, right? This expression is valid when velocity is much less than the speed of the light. But once the speed of that particle is very close to the light speed, we have to use this expression instead. And from this reason, once we substitute the momentum expression into the de Broglie Veblen expression, we're going to have lambda equal to h by p, which is mv divided by, again, square root this factor v by c square, and we move this one to the numerator position, right? Because this is the cascaded fraction. So we move that one, is going to be h by mv. Okay, that's a typical expression for the de Broglie expression, but there is a factor appear here as the multiplicative term 1 by v times c square, right? And if you take a look at this one, you could see that if no particle could move with the speed of light, right? So only the light that has the speed of c. If we consider the photon, the wavelength of the photon is going to be, if this one is c by c is 1, and 1 square appears here, 1 minus 1 is going to remain 0. Okay, and the mass of the photon is also 0. So the total wavelength caused by this is c, right? The speed of the light. The speed of the wavelength caused by photon is going to be 0, right? But this one is not light, it's a particle, which is electron. So we have to consider the case of proton, right? For the speed of electron, once it is 0.999 and c, we could see that it's going to bring us to VE by c as, yeah, you just divide 0.999 c by c, and it's going to remain 0.999, right? So the factor here inside this parenthesis is going to be only 0.999. Yeah, let's substitute everything into this expression. Lambda is h by, oh, I'm sorry for that, I have to substitute the true value. Yeah, it's 6.626 times 10 to negative 34 divided by mass of electron is 9.11 times 10 to negative 31, right? And v is the speed of the electron, which is close to the light speed, right? So it's 0.999 times 3 times 10 to negative to 8, right? Number 8 meter per second, and the square root here is 0. It's 1 minus 0.999 square. Okay, and once you put this number into the calculator, you're gonna get the result as 1.0858 times 10 to negative 13. Okay, negative 13 meter per second. No, sorry, meter. Okay, and you could observe that this is the wavelength, the broad wavelength of the electron that moves very, very fast. Okay, the speed is very close to the speed of the light, and that's the 1.0858 10 to negative 13. If you compare it to the baseball and the electron, you could see that the high speed electron close to the light speed has a shorter wavelength than the wavelength of the electron with 10 million meter per second speed, and it's still quite far from the broad wavelength of the baseball movement here, 10 to negative 34. This one is 10 to negative 13. Okay, it's bigger, it's greater than the broad wavelength of the baseball here, 10 to negative 34. Okay, we complete that example, and that's all about the broad wavelength. Right now, we will see whether the broad theory is correct or not, and the information appeared in the literature is the following. People have found, I'm not sure whether it's okay. People have found the detail, the track or the record like this in 1927. Davidson and Gamma at the Bell Telephone Laboratory. This is a famous and high standard and very competitive laboratory when you work there. These two researchers have discovered the electron diffraction. So once we see the diffraction property of anything, it means that that particle should have also the wave behavior, right? The electromagnetic wave behavior, and diffraction is a kind of behavior of the light, and light is belongs to the electromagnetic wave, right? So that's the first experimental result discovered on Earth or in our world in 1927 in the United States. In another part of the world, in Germany, two people whose name are Esterman and Stan demonstrated the alpha particle. Okay, let's talk about alpha particle. Alpha particle is helium. You know helium, right? Helium is 2, if I can remember exactly. Yes, helium 2. And if you throw away the electron of throw away 2 electrons of helium, you're gonna have helium 2 plus. Yeah, and helium 2 plus, the nucleus of helium is known as alpha particle. Okay, alpha particle. Yeah, you have ever heard this word before, right? In experiment by Rutherford, right, and so on. Yeah, alpha particle has also diffraction behavior. So diffraction behavior was observed by these two persons, Esterman and Stan, okay, who are researchers in Germany. So these two results confirm that the idea or the hypothesis by De Broglie is valid. Okay, is true in reality. Okay, so more experiments reveal the diffraction of low energy neutron and large molecules. Okay, many people, many researchers discovered the same thing: the diffraction behavior of not only alpha or electron, but also the particle, large molecules, neutron too. Okay, and all of these discovery give a strong support to the De Broglie hypothesis. So the De Broglie hypothesis is now become accepted to several people. Okay, that's all about the De Broglie expression. But let's get to another idea or another behavior of tiny particle. The next one is discovered by this person whose name is Werner Heisenberg. Okay, Werner Heisenberg is the person in where is that? Werner Heisenberg. No. Okay, Werner Heisenberg is this person. Okay, if you go to the this person, okay, Werner. Okay, you may pronounce it in English Werner, right? But in German it's called Werner Heisenberg. Okay, Werner Heisenberg is a physicist. Okay, this is in German. I'm sorry for that. Should be in English. So my God, what happened? Where is Wikipedia in English? I don't know how to. Okay, change it to English. EN. Okay, Werner Heisenberg, this one. Okay, he is a German physicist, and he published his work in 1927 in breakthrough paper, and he received also the Nobel Prize due to that expression, due to the uncertainty principle, which we are gonna learn here. Okay, Werner Heisenberg found an inequality for the product of an uncertain coordinate x. So if you have a particle at this location, let's say this is a particle, any particle, right? Let's say it's P, it's not proton, okay, it's any particle. And if you measure it from coordinate 0 and along the x-axis, and this is x location, right? X location, but there is uncertainty whether it's around here, okay? Because when we talk about the tiny scale, we could not know the location of that particle exactly. So this is called delta x, okay? Delta x, the location or along the x-axis. This is the x-axis, okay? So it's not easy to find the exact location along the x-axis of any particle, and that's the idea by Werner Heisenberg. And once the particle, any particle is moving, of course, we cannot measure the speed of this particle easily. There is uncertainty in the speed. And once we multiply the uncertainty or the speed of this particle by m, we're going to have delta p, right? Delta p, which is m. Of course, the mass of any particle is known exactly. M is multiplication of m and v. So Werner Heisenberg found that the product between momentum, which is the product of mass and velocity uncertainty, and the uncertainty location along the x-axis is greater than h by 4 pi. Okay, this is the development further from the Max Planck constant, right? You know that h is Max Planck constant in h by 4 pi only, and if you use the And you know that there is h slash, right, which is h by 2 pi, and that's the expression of the reduced Planck constant. The Planck constant in circular in the circumference way, right? You just divide it by radius of the unit circle, right? Circumference of the unit circle, which is 2 pi, right? 2 pi r when r is 1. Yeah, that's the reduced Planck constant. You're gonna have only half the reduced Planck constant. Okay, that's the product of x location uncertainty and the momentum uncertainty along the x-axis is greater than half the h slash reduced Planck constant. Okay, and that's the formula by Werner Heisenberg. And one of these with a more complicated expression with matrix factorization and so on, that brings that brought Werner Heisenberg to receive the Nobel Prize. Okay, during that era. Okay, what is the meaning from the Werner Heisenberg expression? What is that? Okay, it means in general, neither the momentum, okay, the momentum delta px. Okay, let's draw the idea of this is delta px and the position delta x. Okay, the product of these two terms could not less than, okay, could not be less than this one. Okay, the constant here h slash by 2, or simply the Planck constant by 4 pi. Okay, in of a particle could be measured simultaneously. Okay, the product of these two terms with arbitrarily great precision. Okay, you cannot find the exact location of the tiny particle along the x-axis, and you cannot measure the speed of that particle along the x-axis with any high precision. Okay, it's obstructed by this constant. Okay, and yeah, this is unlike the prediction in classical physics. Okay, you study, you have already studied the movement in the classical Newton scenario, right? You use the h equal to ut plus 1 by 2 at squared. You have u equal to v equal to u plus at and blah blah blah, right? But this one is not these several. Okay, let's draw. You have several Newtonian motion equation, right? V equal to u plus at. You have v square equal to u square plus 2as, right? You have s equal to ut plus 1 by 2 at square, right? This is the Newtonian motion. This is the Newton motion, right? Okay, in Newton's motion, you can predict the location of anything exactly by using this expression, right? But please know that you can use these expressions to only the big object. Okay, you get a great accuracy. But for the small or tiny particle, we cannot apply this. We have to use this expression. Okay, we cannot measure the particle location exactly. We could only predict the uncertainty, okay, which is governed by this constant. Okay, and that's the idea discovered by Werner Heisenberg. Okay, unfortunately, we cannot find anything exactly or precisely. Okay, let's consider the first example by Werner Heisenberg. Werner Heisenberg uncertainty principle. Electron is confined inside a cubical box. What is the cubical box? you have this one cubical box, and one side, of course, cubic has the same distance, right? And one side is 10 to negative 10 meter. Okay, this side is distance along this side is also 10 to negative 10 meter, and also this type is 10 to negative 10 meter. All right, and that's the all. Those are all three sides of the cubic, right? And yeah, that's the first space that we consider electron. Okay, electron is confined inside a cubical box of 10 to negative 10 meter, and on a side, estimate the minimum uncertainty in the x component of the electron momentum. Okay, electron is inside this box, and let's say this one. Electron is inside this box and it's moved somehow. We could not find the location of the electron exactly. We know the electron should be around here with the range of uncertainty as 10 to negative 10 meter. It's 1 angstrom actually. Okay, 1 angstrom. And the next thing is the they want to know what is the minimum entity in the x component, right? So what is delta x in this? What is delta x in this scenario, right? X uncertainty along the x-axis. In of course, we start from the Werner-Heisenberg principle expression, right? Werner-Heisenberg principle expression says we have here delta x times delta px is greater than h by 4 pi, right? Let's use the typical expression, okay, without any fantasy things. Okay, the smallest amount of this product is going to be this one, right? So delta x min times delta px min is this term, h by 4 pi, right? And they want to know what is delta x min, the minimum of delta x. So we're going to move this term to the right hand side, right? So delta x min will be h by 4 pi and delta px min, delta px min 2, right? Yeah, of course, we could substitute all the values into this expression. H is, do we know it or not? Minimum uncertainty in the x component of electron momentum. I'm sorry for that. We need to find delta px min. I'm sorry for that. It's not the case. Okay. They want to know delta px and min. Oh. Delta px and min, what is that, right? So from this expression, we have to move delta x min to this position, right, to this side. So delta x and min, delta px min will be delta x min, delta x with the subscript min. Okay, And now it's time to substitute the value of h, which is the h here, right? This is the Max Planck constant, right? It's 6 to I'm sorry, 6.626 times 10 to negative 34. Oh, 34, not 35. And the unit of this is Joule second, right? And this one is 4 pi. Delta x mean, what is that? The minimum uncertainty of this particle of this electron along the x-axis is one side of this cubic. So it's 10 to negative 10, and the unit of this one is meter, right? Yeah, you put it into the calculator, you're gonna get the result as like this, 5.27 times 10 to negative 25 and kilogram in meter per second, right? Yeah. What is the reason why we have the unit like it? Of course, momentum is the product of the mass and the speed, right? So unit of the mass is kilogram, right? And the unit of the speed of anything is meter per second. That's all in the SI scale, right? And you can adjust it later if you want to explain it in any scale, right? But for the SI scale, we're gonna have kilogram times meter per second like this, and it's very, very tiny, right? The uncertainty of the momentum of the electron particle in this region in 1 angstrom cubical box, right? And yeah, the next thing is what is the kinetic energy of the electron with the above momentum. Okay, they ask us the second. They ask us in the second question, what is the kinetic energy? Kinetic energy of electron. What is that, right? Yeah, the second quantity is the kinetic energy. Let's draw the general expression of the kinetic energy of anything. Kinetic energy is 1/2 times m and v square, right? V square is the speed of that object, right? And because what we know at the moment at this state is the momentum, right? With this value. So if we multiply this term by m and m, okay, we have nothing. We change nothing here, right? Because it's the multiplication by number 1, right? M by m is number 1. If we multiply m and m, the mass of that particle, the particle we are considering, m is going to appear here at the numerator. M will also appear here as the denominator, and it's going to be 1/2 m square v square by m, right here. Okay, so let's get back to the general expression of the momentum when that particle doesn't move so quickly to be close to the speed of the light. This is the general expression of the momentum, right? This expression is still valid, okay? But if you have the particle which moves closely to the speed of light, it's going to be some factor here, right? Okay. And we know that the momentum is m and v, so we could change the expression of the kinetic energy in terms of the momentum right here as the 1/2 in p squared by m. All right, and we would have another expression of the kinetic energy. Kinetic energy would be 1/2 p squared by m. All right, yeah, for the electron Ke is going to be 1 by 2 and delta px mean, right? P the minimum uncertainty of the momentum along the x-axis, and square 2, right? Square divided by the mass of the electron, right? So let's substitute everything. Is going to be 1 by 2, and the value of the uncertainty is 5.27 times 10 to negative 25, right? 25 and square 2, okay, because this is the power of 2 of the momentum. So square for the momentum, and the mass here of electron is 9.11 times 10 to negative 31. Okay, the mass of electron. And yes, we got we'll get it from the calculator as something like this. Minimum, this is the minimum kinetic energy, right? We could get 0.9 0.95, okay, 0.95 25, 0.9525 times 10 to, no, this is already the result in electron volt. Okay, you could convert from joule to electron volt by dividing with the number or the value of the electron charge 1.02 10 to negative 19. Okay, it's going to remain 0.9525 electron volt, and that's the value of the minimum kinetic energy of the electron inside this cubical box, okay, or inside this cubic. All right, so let's move to the next story, to the next next example like this. Okay, we have another example. We have this example, and then we will finish this example to be at the same level as the M604 after we finish this example, right? Okay. Okay, let's consider this example. We have an electron, okay, that is measured to be 5,000 meters per second to an accuracy of very small, 0.003%. Okay, only 3 by 100,000. Okay, that's the ratio. This is very, very small. Okay, this amount, or 3 times 10 to negative 5. Yeah, 3 times 10 to negative 5. And this one is 5,000 meters per second. Okay, that's the speed of the light, or speed of the electron. I'm sorry for that. Let's draw. Okay, once we need to solve any problem in physics, it's better to draw a figure of that particle. Okay, the particle is the electron and it's moving. We don't know exactly the mean value. The mean value of the speed of the electron is we don't know. Okay, we don't know the speed, the mean value of the speed of the electron, but we know the delta V. Okay, delta V of electron is delta V is 5,000. Okay, 5,000 meters per second with the uncertainty. So you have to multiply this one by 3 by 100, right? It's no, it's sorry. So 0.003 by 100 100, right? So it's going to be something like that. And yeah, you just put it into the calculator, right? So it's 50, it's going to be 0.15 meter per second. That's the uncertainty of the electron movement in this scenario. All right, and find the minimum uncertainty in determining the position of the electron. They want to know, we don't know the speed, okay, but we know only the uncertainty of the speed of the electron. And they want to know delta x of the electron in this scenario. Okay, where is the location of the electron? It is really hard to determine, but they want to know the uncertainty location of the electron in this scenario, on this problem. So let's get back to the Werner-Heisenberg expression. Okay, Werner-Heisenberg expression say delta x times sorry for that. Delta px is greater than h by 4 pi, right? H by 4 pi, and they want to know delta xe in this scenario, right? So delta xe is greater than h by 4 pi and delta px, right? So what is delta px in this scenario? We don't know yet, right? But anyway, let's consider delta px. Delta px could be found from the mass of that particle times the uncertainty of the velocity along the x-axis of that particle. So what particle we are considering? What is the particle we are considering? It's the electron, right? It's the mass of the electron times the uncertainty of the electron velocity. So it's yeah, if you use this expression, if you use this relation and you substitute it into this term, right, you're going to get delta xe, which is greater than h in 4 pi and me delta velocity of the electron. Okay, so yeah, that's the case, the final expression, and it's time to substitute all the related values, all relevant values into this expression. Let's open a new page first. Okay. Yes, delta xe is greater than h, which is the maximum constant is 6.626 times 10 to negative 34. Of course, it's 2 seconds, right? The unit for the Planck constant. And let's talk about the numerator. It's 4 pi is nothing, 4 pi. And the mass of the electron is, of course, 9.11 times 10 to negative 31. And it's in kilogram, right? And for the negative, the uncertainty of the velocity is 0.15. That's what we have prepared before, right? Here, 0.15. 0.15 velocity uncertainty is still, it still belongs to velocity unit, right? It's meter per second. And once you put it into the calculator, you're gonna have something like you could have it in this problem, right? Delta xe. Okay, the minimum, which is the right hand side of this inequality, will be 4 pi, and this one is 0.15, right? Delta px, which is that delta px. Delta px is mass and velocity, right? They have already multiplied together. So we end up with the uncertainty along the x-axis by 0.385 millimeter. Okay, this is the quantity scaled already to the appropriate one, which is 0.385 millimeter. Right? And that's it for the first expression of the uncertainty by Werner Heisenberg. It's the uncertain location uncertainty. It's the product. Oh, sorry. It's the product of x location and the momentum. It's the product of location and momentum along the x-axis. Okay, which is discovered by Werner Heisenberg. It's not less than h by 4 pi. That's the minimum limit. Okay, h by 4 pi, and h is the max Planck constant. Okay, we need to stop right here so that it's going to be the same level, same step as M604. Okay, and then I will create the homework. The homework for this week will be the broad wavelength or the Werner Heisenberg uncertainty along the x-axis only. Okay, and that's all for the lecture of today. If you have any questions, just let me know, whether in Zoom, in YouTube, just write down the question. If not, then we need to complete or finish the lecture of today at the moment. Okay, and I'm going to let you know the class attendance result. Okay, I'll see you next year, right? Wish you happy new year, right? Bye bye ครับ สวัสดีครับ I need to stop the Zoom, right? Stop the Zoom.